In this video, we are going to go over the last lesson of the unit, which is on present value of an annuity. And if you think about it, what we're doing is really going backwards compared to the future value of an annuity. So when you were talking about future value of annuity, you had $0 to begin with. Okay, and then you make regular payments or like regular deposits, and then you have this big bag of cash at the end. Okay, so that's future. But in the present value of annuity, you actually have right now, let's try to say right now, I want to draw a big bag of cash. Let's move it down here. So for present value of annuity, you have a big bag of cash right now. And you slowly withdraw until you have nothing left over. Okay, so like I said, you're essentially going backwards. So when will you have this giant bag of cash? Hopefully, you'll have this giant bag of cash when you retire. So the example I gave is Bree and Oscar will withdraw $1,000 per month for living expenses for the next 20 years, and they wonder if they have enough to finance this. The amount in their account will earn 9% annual interest compounded monthly. So basically, they have a plan. They want to live on $1,000 per month for the next 20 years. So how much money do they need today in order to make that happen? So a lot of students, what they will do is they take 1,000 times 12, because there's 12 months a year, and there's 20. They want this for 20 years. So a lot of students will say they need 240,000, and the good news is that they actually don't need 240,000. They need less than that. Why do they need less than that? Because if they have this amount, let's say they have a large amount of cash, they can actually make it grow to 240,000 over that 20-year span. So how can you do this? What you're actually doing is you're finding the present value of each $1,000 withdrawal over the 240 months. Okay, you're withdrawing $1,000 for 240 months. So what you're going to do is you're going to find the present value of the first $1,000, and then the second, and then the third, and then all the way up to the 240th. So just like last time, if you look at the present value of each of these $1,000, you'll see that they form a geometric series. Now before we talk about the geometric series, let's look at the present value of the first withdrawal and the 240th withdrawal. Which one was harder to make happen? Okay, which one was more difficult to make happen? Well, let's find the present value of the first withdrawal of $1,000. Okay, in order to make the first withdrawal of $1,000, Bree and Oscar needed $992.56. That's very close to $1,000. Now, what about the last withdrawal? Wow. Oops, something's off. I divided instead of multiplied. Anyways, there we go. Much better. So, the first withdrawal of $1,000, the present value of that first withdrawal is like $992. Now the 240th withdrawal, you only need $166 right now to make that happen. Why do you need so much less right now to make that final withdrawal of $1,000 because you have, what is it, 20 years to make this happen. So you don't need a large amount to make this happen in 20 years, as opposed to the one that's going to happen within a month from now. Yeah, you need a number that's very close to $1,000. Okay, so that's why seeing this number of 166.41, that's why it would be very, very silly to say that Bree and Oscar needs $240,000 to finance this annuity. So anyways, back to the point. The present value of each of these withdrawals will make up a geometric series. So using the geometric series formula and knowing that A and knowing R and knowing N, you can create the present value of annuity formula. Okay, I would highly recommend you to try to create the formula yourself. Okay, so R is the value of the regular withdrawal. I is the interest rate per compounding period, just like last time. So everything is very similar to what you did in the previous lesson for future value of an annuity. All right, let's do some practice examples. Josh is putting his summer earnings into an annuity from which he can withdraw living expenses while he is at university. He needs $900 per month for 8 months, and that's the rate. So the good news is he doesn't need $7,200. Okay, because the present value of that last, well, of all the withdrawals over the 8 months will not be $900. But they will be pretty close to $900 because 8 months is in terms of compounding, 8 months is really close. Like if I'm talking about 8 years, that's much further along. So 8 months, you're not really giving time for your money to work for you. Anyways, it's better than nothing. Let's find the present value. So 6% compounded monthly. All right. So, perfect. So we're looking at about $7,040.66, which, like I said earlier, is really close to $7,200 because you're only letting your money work for you for 8 months. Okay, so what's the story here? What's the moral of the story? You need to let your money work for you earlier. All right, oops. So, Flora's life savings total to $300,000 when she decides to retire. She plans on annuity that'll pay her quarterly for the next 30 years. If her account earns 5.2% annual interest compounded quarterly, how much can Flora withdraw each quarter? Okay. So this is actually a very scary example. Before I do the question, I want to ask you, is $300,000 a lot of money by the time Flora retires? That is a very, very important question. You need to ask yourself, is $300,000 a lot by the time Flora retires? The math will tell you. Okay, so answer that question because it's very important for us to understand why we are saving. As compounded quarterly. So 4 times a year for 30 years, that's 120 times. All right, when I solve for R, this is the moment of truth. It's a little scary doing this, but you know what? We need to know the truth. Okay. So now let's write the therefore statement first, and then we'll analyze this. $4,950.87 each quarter. Is that a lot of money? Well, here's the thing. Let's see. 4950.87. That's a quarter of a year. A quarter year is 3 months. So we divide this amount by 3. Oops. That's $1,650.29 per month. That's how much you can live on each month. And let's say every month there's about 30 days. Okay? So on average, she can spend $55 a day. And it's all about your expectations in life. It's all about your expectations in life. Is that a good enough amount for you? What do you plan on doing, right? So unfortunately, if this is the number, I don't think Flora should, she doesn't have many options. She can't really travel. She can't go on cruise ships. Yeah, like she can't buy that many. She can't, if she has grandchildren, she can't lavish them with gifts. So you got to be very careful with how you spend it if you have $55 a day. So that was a little shocking because you might think, wait a minute, $300,000, that's a lot of money. But you know what? It's because you need to spread it over 30 years. And here's a shocker. So there's two things working against Flora. What if Flora, good for her, she lives in an unexpectedly really, really long life. If she lives a really, really long life, then this number, she has to spread this $300,000 instead of over 30 years. She should have said over 40 or 50 years, right? The average age average life expectancy is getting greater and greater and greater. So you can't just plan for 30 years. Maybe you should plan for 40 or 50 years. And another problem that I didn't mention is that things get more expensive over these 30 years. So like I said earlier in the unit, $55 a day, right now, it might get you 3 decent meals, but 30 years in the future, $55 a day might not get you 3 decent meals. Maybe it'll get you 1 decent meal. I don't know. It depends on how expensive things get. So that's why when you plan for your retirement, it's much safer to estimate than underestimate, because the worst thing that can happen is that she burns through her funds and she has to, go back to work. Like, that would be crazy, right? So really, really plan for your retirement properly, because I guess instead of going back to work, what Flora can say is, you know what, I'll just live a lifestyle that's very, very different than what I'm used to. Okay. And when you grow up, you'll see that there are a lot of other expenses, right? Like, there's a lot of bills you have to pay that we didn't mention that has to eat up her $55 a day, right? Just living in her house will cost money every day. The gas, the electricity, the water. I don't know, maybe she has Netflix, she has internet, she has phone bills, property tax. All that is a lot of money. Anyways, I hope I scared you enough, so now you'll save up your money. All right, so how much should be in an account today so that the withdrawals of $15,000 can be made at the end of each year for 20 years? I'm going to do one quick little calculation. Is $15,000 a year a good amount? Well, divide that by 12, and then divide that by 30. That's even worse than what Flora had. That's $41.67. So, anyways, we'll do the math. How much does he need today? So to find the present value of the annuity, and it's compounded annually. So what are we looking at here? we're looking at $152 and $152,917.37. If someone retired with this amount, I would say to them, you should probably keep working. This is not a very large amount. If let's say I'm 65 years old and this is how much money I have saved up, my blood pressure would be off like really, really high. I'd be very scared because I don't think that's enough to retire off of. But that, like I said, all depends on your lifestyle and what you want to live, how you want to live. So the present value of annuity is actually a really, really important application question that I want to quickly go over. So usually in my class, I would go to MLS, which is the website that we can peruse through houses, and students always look at these mansions. So one thing I'm really worried about for my own kids is the fact that the house prices just keep going up and up and up and up. It's just the growth is exponential. And unfortunately, salaries are not going up exponentially. So there's a big problem in the house prices. So you know what? Let's say the house price. So I'll let you you could fill in your own numbers. So when my kids grow up, I think that their house price depends on the house they want. But let's say it's $2 million. Okay, that's scary. That is scary. But anyways, the house price is $2 million, and they can make monthly payments. And it's a 25-year amortization, which means my kids will pay off the house over 25 years. Okay, they have a maximum of 25 years. They could pay it off in 10 years, but you'll see that that's probably not possible, especially for a $2 million house. I don't know what my kids are going to do when they grow up, but anyways, it's a 25-year amortization, and usually people make monthly payments, or they make bi-weekly payments. We'll do monthly payments. All right, what else? So we got the house price. We're going to pay off in 25 years, monthly payments. We'll do the interest rate. So we're going to say the rate is 2% per year compounded monthly, which is like an all-time low rate. Like these rates are really, really low right now. And if they were any higher, if they were like 4 or 5%, a lot of people will go bankrupt because they just cannot sustain the payments. So the government has to be very careful with how they touch those rates, because things could go really bad, because a lot of people are overstretched right now. But anyways, so this is actually a present value of annuity question, because think about it. You have this giant chunk of money you owe, in this case $2 million, and then you slowly pay it off until you owe the bank $0, right? So this is a present value of annuity. The present value of annuity right now is $2 million. Well, assuming you didn't make a single down payment. It's a little complicated, because if you're buying a house over $1 million right now, you need a minimum of 10% down payment. So 10% of 2 million, you can already do the math, but that's 200,000. Sorry, minimum is 20% down payment. Oh, that's even worse. So the law says you need a minimum of 20% down payment for houses that cost over $1 million. So you need $400,000 right off the bat. But you know what? We're just gonna ignore that. We're just gonna say somehow you're able to, cheat the law, and you have a $2 million house. Okay. These are scary calculations here, but it's very realistic. Where are we at? We're gonna solve for R. We got that beautiful 2%. So 12 times a year for 25 years, that's 300 payments. The question is, how much is each of these payments? Oh my goodness, maybe I made a typo, but I'm pretty sure I didn't. Let that sink in. $8,477.09. That's just to live in this house, right? There's stuff you gotta pay for. There's property tax, all those bills that I mentioned earlier. Oh my gosh. Wow. And remember, every time you buy a house or buy a car, or whenever you talk about a loan, you should always calculate the cost of borrowing. Just break your heart even more, and we calculate the interest that you paid on this loan. So you made 300 payments of 8,477 and 9 cents. But that is a lot more than 2 million. The question is how much more? So I'm going to take that $8,477.09, multiply by 300, and subtract it by 2 million. So you paid $543,000, $5,403 and $127 in interest. That's actually not that bad. But can you bank on the fact that the interest rates are always going to be this low for the entire 25-year period? I don't know. That time will tell. I can't really predict the future. But right now, the interest rates are all-time low. It's like never been this low. But at the same time, you can argue the house prices have never been this high. So it's really usually one of two things happen. Interest rates are high, house prices are low, or vice versa. So right now we're having really high house prices and really low interest rates. Either way, it's you're gonna pay your money. So yeah, that's how you should always know how to calculate the amount of interest you're paying. What's the cost of borrowing? So we could do another car example. Would be exactly the same thing. You have a giant chunk of money you owe, and you slowly pay off to zero. Okay, so that's the unit.